Hey guys, welcome back to chapter 16. So what we're going to do now is we're going to start diving into determining the pH of a solution. So up until this point, I've given you hydronium, hydroxide concentrations, and I haven't really asked you to think about that at all. But that's not reality. So reality, we've got solutions, and we have to determine what the concentrations are based on those solutions. So finding the pH of a strong acid. So finding the pH of a strong acid, the thing to remember here is that strong acids and strong bases, for that matter, completely dissociate in water. So they completely break apart into ions. So when you have a strong acid, if you know the initial concentration of the acid, you also know the concentration of the hydroxide, or excuse me, of the hydronium ion. So for a strong acid, the concentration of the acid is exactly the same as the concentration of the hydronium ion. And that's because for every molecule of, for example, here, HCl that we put in, it will break apart into its ions. So for every one molecule of HCl we put in, we'll get one hydronium ion out of that. Okay, so by definition, strong acids have the concentration of a strong acid is the same as the concentration of the hydronium. Okay, so this solution, let's hypothetically say that this solution is 0.1 molar HCl. So if I were to ask you what is the pH of 0.1 molar HCl, you need to make the connection that this is one of the big five, that this is a strong acid, and then make the connection that the concentration of this acid is going to be the concentration of that hydronium. So once you make that connection, then we just simply take the negative log of the hydronium concentration. So the pH of a 0.1 molar HCl solution is negative log 0.1 is 1, has a pH of 1. Okay, so that's just the big take home here is strong acid, strong base. The concentration of the acid is going to be the same as the hydronium. Same thing goes for a strong base. So same thing with a strong base. It's going to completely dissociate in water. So the concentration of hydroxide is going to be the same as the concentration of the base. There's a little wrinkle here. So one of the things that I want you guys just to kind of start to put in your head is that bases are always just a little bit more difficult than acids. So we always start our discussion with acids because those are a little bit more predictable, a little bit more straightforward. And then bases always have this little wrinkle or extra step in them. So that's just something to start putting in your brain that, oh, this is a base. It's going to be a challenging question. There's going to be something extra I have to do. So for a strong base, we still see that the concentration of the base and the concentration of the hydroxide are related. So these two are still equal. The extra little wrinkle here is that many bases aren't necessarily a 1-to-1 ratio. So NaOH is in fact a 1-to-1 ratio. So the subscript on this hydroxide is 1. So that's what this number is, number of hydroxides. But we can quickly think of an example like calcium hydroxide. So remember, calcium has a +2 charge. Hydroxide has a -1. So when they come together to form a compound, we flippity-flop the charges, and we get CaOH2. So for this one, when we put it into solution, it'll break apart into one ion of calcium, but it's going to break apart into 2 ions of hydroxide, right? That's what this 2 means. It means there's 2 of these packages. So when we look at the concentration of hydroxide and the concentration of the base, we need to take into account that 2 hydroxides break off of this calcium. So the number 2 would go right here for that example. Okay, so just a little wrinkle, a little additional thing to think about, but not terribly difficult. So if we've got a 0.1 molar solution of calcium hydroxide, the concentration of the hydroxide ion is going to be 2 times that number. So to get to the 0.2, we just took 2 times 0.1. To determine the pH of this, I would probably do pOH, which would be the negative log of hydroxide, so negative log of 0.2. So pOH equals negative log of 0.2 is 0.69. And then remember, pH is just 14 minus pOH. So pH equals 13.3. Okay. So take home from this little discussion here is that strong acid, concentration of the acid is going to equal the concentration of hydronium. For a strong base, concentration of hydroxide is also going to equal the concentration of the base, but just keep an eye on the number of hydroxides. Just peek at that subscript there. So let's end by doing an example. So go ahead and pause the slideshow and determine the pH of this solution, and then determine if it's acidic, basic, or neutral. All right, so here I see a base, so that hydroxide screams at me that that's a base. So I'm going to take 0.0015 molar, and I'm going to multiply that by 2. Why am I multiplying it by 2? Because I see this subscript 2 here. So when this strontium hydroxide breaks apart, it's going to release 2 molecules of hydroxide. So multiply that by 2. So 0.0015 times 2 is 0.003. And that's going to equal the concentration of hydroxide. So first, I'm going to go to pOH. So negative log of the hydroxide. So pOH equals negative log 0.003, 2.5. And then ultimately we want to know the pH because that's what it's asking for. So pH is just 14 minus pOH. So pH equals 11.5. So is this solution acidic, basic, or neutral? So pH is greater than 7. This is going to be a basic solution. I hope you guys found this helpful.